Hey folks, and welcome to today's lecture. So if you remember our discussion from last time, we addressed the particle on a line model, which describes a particle that's subject to the potential, it's a piecewise potential, v of x is equal to 0, assuming that the particle is between the bounds 0 to L, or plus infinity otherwise. And so our physical model of this kind of looks like my tape dispenser in this little cardboard tray. It can move around in one dimension and only in one dimension, and assuming that the walls of this cardboard tray were infinitely tall, that would help us encapsulate the fact that this particle can only move in one dimension and it can never escape outside of this boundary between 0 on the one hand and L on the other hand. And so what we learned from quantum mechanics is that the wave function that describes this particle in between our bounds 0 to L is a sine function. And not only is it a sine function, but there is an integer n called a quantum number that shows up in our sine function that restricts values of the wave function to certain integer or certain quantized values. And that really puts the quantum into quantum mechanics. We also learned that each particular solution to the wave function, of which there are many solutions, each with a different value of n, are given by the energy expression E sub n is equal to h bar squared times n squared times pi squared divided by 2ml squared, where m represents the mass of the particle, not notably the mass of the box. So both the wave functions and the energies in this case are quantized, and it was as a direct result of the particle being confined to a line of finite length. So what are we going to do today? Well, we don't live in a one-dimensional world. We in fact live in a world that is in 3 dimensions. Typically, we expect particles to be able to move around in the x dimension, the y dimension, and the z dimension. And so that's what we're going to talk about today. We're going to first start by generalizing the time-independent Schrodinger equation from its one-dimensional form to its 3-dimensional form. And then I'm going to introduce to you a new mathematical technique called separation of variables that will allow us to take what we learned about the particle on a line model, its solutions to the wave function and to the energy expression, to treat systems of higher dimension. So we'll start with the 2-dimensional case. If you like, we can call it a particle on a plane, although unfortunately not this kind of plane, just a 2-dimensional surface. And then we'll talk about the particle in a box model, which is what our particle can do, assuming that it's allowed to move about in the x, y, and z dimension. So much closer to how systems behave in real life. And then last but not least, we're going to talk about a concept called degeneracy, and we're going to discuss how symmetries in the wave function give rise to this degeneracy property. Now, as always, there are many good references out there for trying to learn this information, and so much of today's lecture is based off of your Atkins textbook, topic 7D.3, as well as we're going to make pretty heavy use of this Chemistry LibreText website, and I'll put the exact links that we use in today's Moodle readings, but it's going to be a really great website, and I found it, both in terms of the text and in terms of the graphics that are present, a really helpful way to try and understand the information that I'm about to present today. Okay, so let's talk about the 2- and 3-dimensional time-independent Schrodinger equations. So way back in lecture 2, we talked about the one-dimensional Schrodinger equation. And we derived that Schrodinger equation by thinking about the energy thinking about the one-dimensional Schrodinger equation as arising from a statement about the total energy of the system. So we have that E times psi is equal to h hat, so this Hamiltonian operator times psi. And our Hamiltonian operator is a sum of the 2 pieces of energy that make up the total energy of any system. T represents the kinetic energy operator, and V is our potential energy operator. And even more specifically, we were able to give explicit expressions for t hat and v hat. And the way that we did that back in lecture 2 is that we took our basic operators, which we had an operator for x, an operator for p, an operator for t, and an operator for e, and for our kinetic energy, we said that since T, according to classical mechanics, is 1/2 mv squared, or p squared over 2m, and that implies that T hat is going to be the momentum operator squared divided by 2m. And since my momentum operator is negative IH bar, partial derivative of whatever the function that appears to the right of it is going to be, dx squared, that's where we get this t part of my operator. So that negative h bar squared over 2m, d squared dx squared, that's my kinetic energy piece. And then, much more boringly, since v is just some function that is system specific and that we'll have to identify more in later, then that means that v hat is equal to v of x hat, but x was our really boring operator. Anytime you see an x hat, you just put back in an x. And so our potential energy operator gives rise to this v of x portion of our Hamiltonian. And so I say that partially as review, but also to motivate how the Schrodinger equation is going to change once we start talking about motion in 2 and/or 3 dimensions. So what changes about kinetic energy when we tackle 2-dimensional motion? Well, we have momentum in the x direction, and we also have momentum in the y direction. And those sources of momentum and the kinetic energy that it leads to are additive. So if I have a certain amount of kinetic energy that arises from motion in the x dimension, I can add that to the amount of kinetic energy that arises from motion in the y dimension, and the sum of those two quantities is going to give me my total kinetic energy. Same thing for motion in 3 dimensions, by the way. And so all that we have to do is now treat our momentum operator in the x direction and our momentum operator in the y direction. And the only thing that's different about these operators is, whereas before I was just using x, now I'm going to use d squared dx squared for the x dimension, but also use d squared dy squared for the y dimension. And just like above, my 2-dimensional version of the potential energy is still quite boring. The operator for y, since it's also a position-based variable, is just y hat is equal to y. And so I don't really need to change anything about my potential energy operator. So this gives rise, in summary, to a Hamiltonian that is still the sum of kinetic and potential energy, but now is a sum of kinetic energy in 2-dimensional motion and potential energy that could vary based on x and y. And so that gives me what I have shown in this box, which is my 2-dimensional version of the time-independent Schrodinger equation. And so it looks very similar to the 1-dimensional version. The only things that have changed is that now my wave function can depend on x and y, and my potential can depend on x and y. And I have one more term in my kinetic energy piece that gives me the partial derivative, the second partial derivative of the wave function with respect to x, plus the partial derivative of the wave function with respect to y. So if we want to generalize this to the 3-dimensional case, it's not too hard, aside from it involves a lot of writing, so your hand might start to cramp a little bit. So we have our Hamiltonian, which now we've tacked on a z-specific piece, since our 3rd degree of freedom in terms of different dimensions of motion is that z dimension. And it looks exactly the same, And the only thing that you might see differently in a textbook is that this is about the point at which chemists get really tired of writing all these partial derivatives. And so we have taken to calling this operation what's called the del operator. And so you may see this same expression either written as the first line that I have in the box where you show out all of these partial derivatives explicitly, or you just might see the del operator. And anytime you see that upside down triangle, which is called a del, you know to put in d squared dx squared plus partial second partial with respect to y plus second partial with respect to z. Okay, so not too bad conceptually, definitely a little bit more writing. You can kind of see why we started off with a one-dimensional case, but this is our new Schrodinger equation. And that gives us permission to start talking about not just the particle on a line, but the particle on a plane. Motion in 2 dimensions. So now let's consider a particle that is confined to not a one-dimensional location for its motion, but a 2-dimensional system. So I've drawn a mathematical picture of it at the right. You can see that just for generality's sake, I don't necessarily have to guarantee that this plane is a square. So I've said that we have one length, the length of the box, the length of the plane in the x dimension we'll call L sub x, the length of the plane in the y dimension we'll call L sub y, and the particle is allowed to move in both the x and y dimension, but we're not yet letting it move in the z dimension. And so I tried my best to, using household objects, come up with an example of this. So this is the top of a tea tin that I have. And what we're going to do, so we still have my particle, we're going to allow it to move in 2 dimensions, but we're not yet going to allow it to move in this 3rd dimension. So again, I've picked an object where the walls of the container are pretty small so that you can see the particle as I'm moving it around. But for this to truly match the potential that I have shown on this slide, we would need the walls of this container to be infinitely tall so that we can guarantee that the particle will never be able to escape this system. As it stands, since it's fairly small, I only need a tiny bit of energy for the particle to be able to escape. So this is what our 2-dimensional particle on a plane looks like, but with much taller walls to the system so that we can prevent escaping. So just like in the 1D case, we can look at this potential and immediately make a statement about what the wave function looks like outside of the bounds. We know that in my case where there's an infinitely tall set of walls here, I have 0 chance of finding the particle outside of these boundaries. And so since the probability is equal to 0 finding the particle over here, that means that its square root, the wave function, is also equal to 0. Inside of the bounds, we're going to have to do the work of solving the Schrodinger equation, this time using the 2-dimensional version of the time-independent Schrodinger equation. And so, because the potential is equal to 0, this v of x comma y term is going to go to 0 and we don't have to worry about it, but still it looks more complicated than what we saw in the 1-dimensional case. There are more variables and more terms showing up. So it may lead to you thinking to yourself, like, can we even solve this? And just did so much work for the 1-dimensional case, can we reuse some of that work maybe, or some of those insights in order to tackle the 2-dimensional case? The answer to both of those questions is yes. And so let's go ahead and get to it. So with that, we're going to have to take a small aside to talk through what is a fairly mathematical derivation. And so I want us to pause, take a deep breath, and I'll try and walk us through the math for it. And then at the end of the math that I go through, I'll give us some of the big takeaways so that you can see why it is that we want to use this separation of variables technique, and it's going to lead us to a pretty familiar looking result. So there's going to be a light at the end of this mathematical tunnel. Okay, so separation of variables is not specific to PChem. It's used all the time in the study of what's called differential equations, which is the study of equations, just like the Schrodinger equation, where derivatives show up in the equation itself. The fact that we are calling this a partial differential equation is because we have partial derivatives instead of just ordinary derivatives that are showing up in our equation. And there is a technique, or if you like, an axiom in differential equations that says that when you encounter a system that has more than one variable showing up, and the derivatives that show up are what's called linear, so we like add the second derivative of the wave function with respect to x to the second derivative of the wave function with respect to y. We don't multiply them or divide them or do anything funky like that. We just add them up. That means we can assume, or really at this point it may just be a hope, that our solutions to the wave function are going to take a special form, which is that the solutions will be a product of two functions that we can solve for. The first function is something that will only depend on x, and the second function is something that will only depend on y. Now, in terms of what letters we should choose to represent these functions, it's really arbitrary. So if you like, we could have done f of x, g of y. Your textbook uses capital letter X and capital letter Y, so that we'll constantly be reminded of the fact that our X function depends on X and our Y function depends on Y. So I'm going to use that notation, but I know I'm running the risk of us forgetting that little x or little y refers to a variable and capital X or capital Y refers to a function. So if in your head you need to make capital X the function like f of x, and the function capital Y, g of y, just to keep things in your head straight and kind of mathematically consistent with what you're used to. No harm in doing that. So some of you, this will let me know there's probably two categories of students in the room. Some of you look at this and are like, okay, Dr. Vivi, I don't really know why we're doing this, but I'm willing to just forge ahead. And some of you, and I was in this latter category when I was a student, looks at this and is like, I don't feel comfortable with this as a guess. I have no reason to suspect that the solutions to the wave function should take this form. So why should I proceed with this guess when really it just kind of seems like we're making up math at this point? And my answer to that is that in differential equations, guess and check is our best friend. And so we're going to try this. We're going to plug this solution, or really this like template for a solution, into the Schrodinger equation, and one of two things is going to happen. Either our math will kind of just barf and give us psi is equal to 0. There are no solutions to something when you try and cast it into this form, in which case we'll say, okay, well I know it's not psi of 0 because I know the particle is somewhere, so this solution is non-physical, we'll have to try something else. Or we're going to end up with an interesting solution, a non-trivial solution, and we'll be able to take that solution, plug it back into the Schrodinger equation, and via this like kind of guess and check process, we can make sure that the solution works. And if the solution works, it works. We're kind of done at that point. And so I hope with that statement, you'll allow me to forge ahead with this template for a solution, and you'll see that in fact, this is going to work for us, and it's going to allow us to, without too much effort, be able to solve the two-dimensional particle on a plane problem. Okay, so forging ahead, remember what our solution is for the two-dimensional Schrodinger equation. We need to set E times psi equal to negative h bar squared divided by 2m times the second derivative of psi with respect to x squared plus the second derivative of psi with respect to y squared. So this line right here is just the time-independent Schrodinger equation. Haven't done anything fancy yet. The next thing I need to do is I now have an expression for psi, and so I should substitute that in on my right-hand side anytime I see a psi. And remember that what we are claiming psi is equal to is a function x times a function capital Y. So if I do that substitution everywhere, still haven't done anything too mathematically interesting, but I end up with what you see in the second line of this derivation. Now in this third line, this is where we're going to have to get interesting. So our third line, let me go ahead and erase this orange momentarily. I'll put it back in a second. Our third line of our derivation now we're going to make use of a fun fact about partial derivatives, which is that if you have a function that doesn't depend on the variable that you're taking the partial derivative with respect to, it's effectively just a constant, and you can pull it out of the derivative. So in my first term, I'm taking the second derivative of x times y with respect to x. So the y is a constant, and I'm going to pull it outside of my derivative. So my y is a constant, and I'm going to put it on the outside of my derivative. And I still have to leave the d squared x by dx squared term because I don't have anything more substantial that I can do to simplify that expression. But I do know that the y function can be moved outside of the expression. Similarly, when I get to my second term, I'm taking a partial derivative with respect to y, and so this x function can be moved out in front of my second order differential equation. And that gives me the second term on the third line of my derivation, which says that my function x times little x times whatever the second derivative is of my y function with respect to y, that's my second term. And now that I've done that, I want to clean things up a little bit. And it's kind of always nice in math if you can take all of your terms that show up on both sides of the equation and divide them through. And so in an effort to clean things up, I am going to divide now both sides of the equation by my x function and my y function. And once I do that, that will cancel out nicely with on my left-hand side, and I'll just be left with the constant e. And on my right-hand side, well, these two y terms will cancel out. I'll be left with a factor of 1 over x function, still times that second order differential equation. And as for my second term, now the x functions will cancel out nicely, and I'll be left with 1 over my y function times the second order differential equation of y with respect to y. Okay? And so this is kind of the end of our algebra sequence. So now we have to think about this one a little bit. The thing that I want us to notice in particular is that we have on the left-hand side a constant. Energy is equal to a constant. And on the right-hand side, I have two terms. The first term, which I've shown in green, depends only on x. And the second term, which I've highlighted in blue, depends only on y. Now, why is that interesting? It's because I can make a fairly bold claim about this. My claim is that the equation above, the last line of my derivation, can only be true if the first and the second term, so my term that I've kind of bracketed in green and the term that I've bracketed in blue, are both individually equal to constants. This is probably the conceptually most tricky part of today's entire lecture. So let's go in and give a concrete example as to why this must be the case. So let's kind of play around with this function a little bit. Let's assume that I want to claim, maybe kind of a proof by contradiction, that my term that shows up in green is not equal to a constant. In other words, if I plug in, for example, x equals 1, maybe my function returns something like the number 7. And if I plug in x equals 2, maybe I'm just tossing around some numbers as a way of example. Maybe my function returns the number 10. Well, so that part of my function can change then as a function of x, assuming that this whole term is not just equal to a constant. It's not just a constant function. And what that means is that I can vary this part of the function, and if I don't change my value of little y, that would imply that my left-hand side of the function, e, is not constant, that it can also change. So if my first term changes, that means that in principle, my left-hand side could change. But we just said that no, the left-hand side is equal to a constant. And so clearly that can't be the case. My x function, or this term that shows up on the left, it can't actually be anything more interesting than just a function that's equal to a constant. Similarly, for this term in blue, if I allowed it to vary, I said it was not a constant function, and I said, okay, well, let's see, if y is equal to 3, maybe my function returns back for me square root of 5i, and you're telling me this function can vary, so if I plug in a different value of y, then the function could change its value. Well, that means that if I were changing y and holding x constant, that the left-hand side of the expression would change. And we know that can't be the case either. So clearly, this term that I've highlighted in blue can't be anything other than a constant. And so the specific numbers that I plugged in for the functions was a way of me just trying to make this example concrete. Obviously, I don't know nearly enough about the x function and about the y function in order to say what the inputs and outputs should be. But I do know enough to say that because both of those could potentially vary independently, and we know the overall result has to be equal to a constant, the only way that we can make that happen is if both the green term and the blue term are themselves individually equal to constants. So now that we have established that logical claim, now we can go ahead and make a statement about what these functions will look like. So I'm going to take my green function and I'm going to set it equal to a constant. I don't know exactly what to call that constant, so arbitrarily I'm going to call it e sub x, although we'll see in a moment in the lecture I'm really calling it e sub x because we'll find that that corresponds to the energy component that's due to motion in the x dimension. And then I have a second equation, my blue equation, that says that we're going to set this blue term equal to a different constant. We'll call it e sub y. And just like I've shown in the last line of the derivation, it had better be the case that whatever my constant e sub x is and whatever my constant e sub y is, they had better add up to give me back e, the original constant that I started with. So these are our three constraints on the system. And now I want us to notice something. For equation 1, for example, some of the letters have changed, right? Our equation now says that I'm taking this expression with respect to my x function instead of psi of x. So the letters are different, but the equations are identical to what we were solving in the one-dimensional particle in a box case. And to see that, because you're like, wait a minute, this looks a little bit different. I thought it was supposed to be e psi equals negative h bar squared over 2m. You're absolutely right. I just need to move over and multiply both sides of equation 1 times my x function to give me e times the wave function with respect to x is equal to negative h bar squared over 2m d squared, the x portion of my wave function, dx squared. And similarly for my y function, if I multiplied equation 2 by on both sides by y, then I would get that e times y, in this case instead of psi, is equal to negative h bar squared over 2m times d squared y function with respect to my y variable. And so the letters we used are different, but the expressions are the same. And so the solutions to this set of equations, and we're going to be able to solve both equations independently, is identical to the solutions to the 1D particle on a line case. Hooray, right? We don't actually have to do any more work in order to say that the solution to my x function is square root of 2 over, in this case, L sub x, since we said that the length in the x dimension is the variable L sub x, just so we can put in all of our little subscripts to denote whether we're talking about the x part or the y part, times sine of n pi x over L times x. And you'll notice that because x and y are operating independently, there's no reason to suspect from these solutions that our quantum numbers all have to be the same. So I'm going to denote the quantum numbers that respect to the x degree of freedom, n sub x, and the quantum numbers that relate to the y degree of freedom, n sub y. And so similarly, the y function looks identical. It's just I'm using subscript y now in this case instead of subscripts x. And just like in the 1D particle in a box solution, the energy expressions are also identical. We're just going to be pretty careful with our subscripts. That means if we scroll all the way back to the top, when we started this nonsense about separation of variables, my wave function, that is a function of both x and y, is a product of the x function times the y function. And my energies are a sum of the x part of the energy and the y part of the energy. And that means for us that the text in green is my overall grand finale solution to Schrodinger's equation for the two-dimensional particle on a plane problem. I have two sine functions, one that depends on x and one that depends on y, multiplied together. And what's really interesting and worthy of note is that because we started talking about confined motion in 2 dimensions, we arrived at 2 distinct quantum numbers. And in general, each degree of freedom, here x and y are our 2 degrees of freedom, leads to a distinct quantum number. So ask yourself real quick, how many quantum numbers, distinct quantum numbers, are we going to get when we start talking about the 3-dimensional particle in a box problem? And if you answered 3, you're spot on. That's exactly what we're going to see. Before we talk about the 3-dimensional solution, I want to do a quick demo of being able to visualize these solutions and trying to plot 3-dimensional functions. Again, here we're trying to think about x, y, and psi is beyond the limits of my art skills. So we're going to hop over to chemlibretext.org, and they're going to give us some graphics that will help us visualize this problem. All right, so here's ChemLibreText. Here's our 2-dimensional particle in a box problem. I'm going to skim over this text because it's identical to what we just went over, although it is a very nice description, so you might want to take a look at it over your own time. And what I want to focus on is this visualization of our solutions to the 2-dimensional wave function. On the left-hand side of the screen, you're going to see what's called a contour plot. It's kind of like if you've ever seen a topographical map. There you can draw lines representing where the wave function achieves certain magnitudes or certain values, and then plot that in a 2-dimensional plot. It's giving the same information as the plot to the right, which is a 3-dimensional plot that if I drag my finger along this website, I can kind of scroll around and rotate the plot. But where it starts to look like the 2-dimensional plot is if I drag it so that I have x and y showing up in the plane and my values of psi going outside of the plane. And there maybe you can see where my contour plot is coming from. And so now as I've rotated it, the contour plot on the left and this 3-dimensional plot look identical to each other. And I've got these little sliders on this plot that help me visualize for different quantum numbers how this plot changes. So in my ground state, where n sub x is equal to 1 and n sub y is also equal to 1, we get that my function kind of looks like a cone. If I were to make a contour so that I'm just looking down the x-axis, you'll see that this kind of looks like, it's a little hard to scroll and zoom, so I apologize if I'm not able to do this. You can kind of see, although I made it a little bit crooked, that this still looks like a sine function. It's just that it also looks like a sine function from this direction. If I increase my value of one of my quantum numbers, now along this x direction, this looks like the n equals 2 solution we saw from the particle in a 1D box case, where we have our wave function go up, pass through a node, dip back down into a negative value of the wave function, and then come back to 0. And maybe unsurprisingly, if we further increase the value of my x quantum number, so n sub x, then my n equals 3 solution also looks like what I saw in the one-dimensional case. Now that I have n equals 3, I've got 1, 2, 3, 4 nodes showing up in my problem. And where things start to look kind of fun/complicated is when I start to deal with larger values of n sub y as well. So you can see that this wave function starts to have many different peaks and troughs to it, and not only do we just have nodal points in this two-dimensional case where there's one particular coordinate for x and y that leads to the wave function being equal to 0, but we in fact have what's called nodal lines, where there's entire lines across the surface in which our value of psi is equal to 0. And so this is kind of interesting and fun for us. And what I want to show as one last thing before we move back to our slides and start talking about a concept called degeneracy is something to note that's interesting about the symmetry of this wave function. So let me go back to the n equals 1, 2 case. So in this case, this is what our wave function looks like if n sub x is equal to 1 and n sub y is equal to 2. So we've got kind of two halves to this wave function, one where the wave function is going up and one where the wave function is going down. And if I rotate it, then it just kind of looks like the wave function is all doing the same thing. If I switch these, so now let's make n sub x equal 2 and n sub y equal 1, notice how the wave function looks the same as before in terms of its shape, just rotated 90 degrees. So if I were to scramble this around and hide what's x and what's y, you wouldn't be able to tell if this was the n sub x equals 2, n sub y equals 1 solution, or if it was the n sub x equals 1, n sub y equals 2 solution. And that type of symmetry in the wave function, we'll see in a second, leads to a really interesting property when it comes to talking about energies. All right, so let's hop back to the notes. We just started talking about the case, and what you were seeing in the graphic was talking about when the potential is symmetric. So what happens if we have a square plane that the particle is allowed to move in, such that the side length in the x dimension is equal to the side length in the y dimension? In that case, there are various solutions to, or various sets of quantum numbers that lead to the same energy. So for example, what we just went over was the case where we have one of our quantum numbers is equal to 1, one of our quantum numbers is equal to 2, and it doesn't matter kind of which is which, both cases will lead to the same energy. In this case, it leads to an energy of 5 times h bar squared times pi squared over 2 ml squared. And it's really interesting. So interesting, in fact, that we call this phenomenon of distinct wave functions leading to the same energy, we call that degeneracy. And it has all sorts of interesting implications for chemists. And as a foreshadowing of where we're going to go in this course, if you remember your p orbitals from general chemistry and how we have 3 distinct p orbitals, different orbitals, but they all have the same energy for atoms, those are distinct wave functions leading to degenerate energies. And so I want to bring this up right now for the particle in the box case, kind of to define it, but also just in recognition that degenerate orbitals are hugely important to our everyday topics in general chemistry, because it really matters that we have 3 p orbitals that all have the same energy in terms of what atoms do we expect to have unpaired electrons, which ones do we have to expect to have paired electrons, Hund's rule. All these concepts in GChem really depend on this idea of degeneracy. And so there are 2 types of degeneracies that you'll see in chemistry. One, and really what we're going to focus on in PChem, is something called formal degeneracy. So in a system that has symmetry, in this case our symmetry is that L sub x is equal to L sub y. When that symmetry occurs, sometimes you'll get solutions to the wave function that look identical, just like we saw a moment ago, but that are different based on like a rotation or a reflection or something along those lines. In those cases, those energies corresponding to those wave functions are going to end up identical because of that deep underlying symmetry. And so that distinct wave functions that look identical except for maybe a rotation leading to identical energies is what we call formal degeneracy. It's degeneracy or identical energies that arises as a function of symmetry. The other type of degeneracy that we might see is something called accidental degeneracy. So accidental degeneracy is when two states of a system, two solutions to the wave function, have the same, or in spectroscopy, if they have close enough energies that your instrument can't really detect the difference, we call those accidental degeneracies. There's nothing that is underlying why those two states have the same energy. There's just something that was kind of happenstance about the parameters of the system that for a particular moment, maybe a particular moment in time, or a very specific length of the box that you picked, you get two states that end up having the same energy. The Chem Libre test gives you one example of accidental degeneracy that arises for our particle in a box system if we choose very specific values of n and very, very specific values of L, but I'm not going to go into detail on that. The analogy that I want to give is that talking about degeneracy is kind of like talking about birthdays. So formal degeneracy might be a case in which you learn two people have the same birthday and you ask them about themselves and you learn they're twins. Of course they have the same birthday. There's something that caused that, and that was them having the same mom, the same, X and Y chromosomes. They get the same birthday. Sometimes you might also walk into a room, and if you've ever been in this situation, you might learn, wait a minute, someone that I know shares my same birthday. It's not really anything special. It's just there's only 365 days out of the year, and there's 7 billion people. So from time to time, you're going to meet somebody that has the same birthday as you. Not because you're related, not because you necessarily have any connection, but you just happened to have the same birthday. So formal degeneracy and accidental degeneracy works in the same way. If you learn that two wave functions give rise to the same energy state and they're symmetric with one another, you call it a formal degeneracy. If you notice that they have the same energy and you can't find anything that's common about the shape of those wave functions or some mathematical property about them, then you just call it an accidental degeneracy and you move on. Okay, so where I want to wrap up today is with what either feels like a grand finale or a letdown. I'm not sure which. It's the particle in a box, motion in 3 dimension. So here I have the rest of my tea container now. And the way that I can give a physical system that matches a particle in a box is to take my particle, I'm going to put it inside my container, and I'm going to close the lid. So now this particle, as long as I hang onto this lid really tightly, can move around in 3 dimensions. It can go anywhere it wants to inside of this box, but there is a really strong metal barrier that's preventing the particle from escaping this box and going outside of it. And so mathematically, that gives rise to the equation that I've written in purple for the 3-dimensional solution to this particle in a box potential, which says that the potential is 0 anywhere inside of the box and infinity anywhere outside of the box. And so that we're really careful with our notation, because again, there's no guarantee that no reason why I have to demand that my side lengths for this cube are all the same. I'll give the notation L sub x, L sub y, and L sub z to talk about the different dimensions of the box. And so, just like before in the 2-dimensional case, we could go through the whole separation variables technique one more time. I'm not going to do that for us. What I am going to say is that the solution ends up being a product of 1-dimensional wave functions. In this case, it's a product of the x component, the y component, and the z component, So we have a three separate sign terms showing up in our equation. And once again, our energies are an additive energy based on the x portion, the y portion, and the z portion. And so what I've shown in this green box is my 3D particle in a box solutions. Now, I already struggled a little bit trying to show us what plotting the psi versus x versus y looked like when I had 3 dimensions of data to work with. Now I have 4, and those are tricky / impossible to visualize, and honestly, it doesn't give us too much more information compared to what we already said about the 2-dimensional case. And so this is mostly where I'm going to end the lecture for today. The only thing that I want to show, just because it's kind of symmetric and pretty, is showing the energy level diagram for the specific case where all of the sides of my cube are identical to each other, in which case you get an energy level diagram that has a lot of nice degeneracies. And on this slide, I'm drawing kind of a single line to indicate that is one distinct solution to the wave function. And I put in green underneath some notation so that I can index what my quantum numbers are for each state. So you can see I have the 1, 1, 1 state, I have the n sub x equals 2, n sub y equals 1, n sub z equals 1 state that is kind of in the middle left, and a couple other states. Just like we did in GChem, I'm spreading these out along the horizontal axis just so that you can clearly see the different solutions. But this is a one-dimensional plot. It's just showing the different energies. And in this case, starting to be just a teensy bit reminiscent of p orbitals that we saw from GChem, I see that I have a couple different states in my 3-dimensional particle in a box that are of identical energy. And the terminology we would use to describe this is that since I have 3 different states in this case that all have the same energy, I'm going to say that that is threefold degenerate. And if that's starting to remind you of p orbitals, which are also threefold degenerate, there's going to be a reason for that. And once we finish talking about the particle in a box, which will take us still another lecture or 2, then we're going to start talking about the hydrogen atom. And that's really where we're going to make the connection between the properties of the wave function that we're talking about with the particle in the box suddenly to take on the exact quantitative form that you're used to from GChem when we started talking about s and p orbitals. So that's where we're going to end today. And I want to wrap up with a summary, which says that using our separation of variables technique, we found the solutions to both the 2-dimensional and 3-dimensional versions of this particle in a or on a blank problem, or if you like, the infinite square well. So we've got particle on a line, particle on a plane, particle in a box. And those solutions are products of the 1-dimensional wave function in order to get the overall multi-dimensional wave function. And they're summations of the 1-dimensional energies to sum up to the total energy of the system. And importantly, that kind of product for the wave function, sum for the energies, is going to hold true in a variety of systems, really any time we employ the separation of variables technique. The other important takeaway from today is that each degree of the freedom in the system gave rise to a unique quantum number. So in the 2-dimensional case, we had 2 quantum numbers, and in the 3-dimensional case, we have 3 quantum numbers, n sub x, n sub y, and n sub z. And then last but not least, special things happen when you get symmetries in a potential. Symmetries in a potential frequently lead to rise to symmetries in a wave function. And when we have wave functions that have identical shapes but maybe are rotated differently, that means that we get states of degenerate energy. And we learned in this class how to classify some of those degeneracies as formal degeneracies and some of those degeneracies as accidental degeneracies. And so with that, that's going to be it for today, and I'll look forward to seeing you all in class. Take care, folks.